Okay, here we are back for part B, and we're continuing on from where we left off in part A. Part number 2 here says, according to the rules, how many significant figures do the following measurements have? And it says the answers are on the next page, but don't look yet. So the first one is 45.20 meters, and the second one is 0.007609 seconds, and 97,420 meters would be the third one. So again, looking at significant figures, non-zero digits always count as significant figures. Zeros are the big question. And so remember, the rule for zeros at the end of a number is that 0 at the end of a number does count if there's a decimal point anywhere in the number. So there you go. 4 significant figures. For this number here, those zeros at the beginning never count. They're just there to locate the decimal point. Okay, so those don't count. The 7 and the 6 obviously count. The 0 counts because it's between numbers that are not zeros. And the last 9 obviously counts. So that's 4 significant figures. 97,420, let's see, 9742 obviously count. What about the 0 at the end? I'll give you a moment to think about it. Tick tock, tick tock. There's no decimal point at the end of this number or anywhere else in the number, and so the 0 at the end does not count. And so that's, again, 4 significant figures. What do you know? Number 3, okay. According to the rules for addition, to what decimal place should the sum of 23.41 centimeters and 12.2 centimeters be rounded? Okay, we've got 2 decimal spaces here, which means we have tenths and hundredths. But here we've only got 1 decimal space. So that's going to be the deciding factor. And that means the first decimal place would be the tenths place. And what is the result of this sum? Well, let's see, 34, what you get is 35.61. But that it has 2 decimal spaces. So that's not right. We have to round it off so that it has 1 decimal space. So that means the second decimal space has to go. It's a 1, meaning it's less than 5, so it doesn't affect the numbers before it. So 35.6 centimeters would be the answer for that one, for the correct number of significant figures. Okay, number 4 is about area. Area is length times width. Okay, area is length times width, as I mentioned. So let's see, where were we here? Okay, so if we've got 305 meters times 27 meters, first of all, we want to know how many significant figures the answer should have. Well, 305, the 3 and the 5 obviously count, and the 0 counts also because it's between numbers that are not zeros. So that's 3 significant figures. And the 27 obviously has 2 significant figures. And so that wins. The answer should have 2 significant figures. If you multiply these numbers together on your calculator, though, you get 8,235 square meters. That obviously has 4 significant figures. If you're going to be picky about, well, I mean, if you want the correct number of significant figures, let me put it like that, you have to round this off to 2 significant figures. That means the 3 and the 5 have to go. The 3 is the first number being dropped. It's less than 5, so it doesn't have any effect on the numbers before it. So we have 82, but no, 8,235 does not round off to 82. Remember, if you drop any numbers before a decimal point, and there is an implied decimal point at the end of the number, if you have a number that has no decimal point written in it, you can assume that the decimal point is at the end. So the decimal point is implied after the 5. If you drop any numbers before the decimal point, you have to replace them with 0. So it's 8,200 square meters. That's the correct number. But don't actually write the decimal point in, because then 8,200 becomes 4 decimal points. And in fact, I put the dot over the I in a position that it looks like a decimal point. So no, that is not a decimal point. It's 8,200, no decimal point. Okay. We want to round this number, 348, so that it has 2 significant figures. Well, that means the 3 and the 4 can stay, but the 8 has to go. The 8 is greater than 5, so that means the digit before it has to go up by 1. And the 8 is also before the decimal point, so it has to be replaced by a 0. But in the new number, do not put a decimal point in here, because this number currently with no decimal point means that the 0 at the end doesn't count. That makes this number 2 significant figures, just like we wanted. If you put a decimal point in, it will be 3 significant figures. So watch out. Okay, the next page is the answers to the previous page. So we'll skip that. And then we skip on to scientific notation and metric prefixes. And that would be this page right here. Scientific notation and metric prefixes. Although I don't know if we actually get to the metric prefixes just yet, but we'll do scientific notation anyway. And okay, scientific notation. Scientific notation is used because it's a convenient way to write numbers that are very big or very small. And that's one thing that I often try to point out repeatedly to beginning chemistry students, or physics students for that matter, is that in chemistry and physics, one thing that you have to get used to is dealing with quantities that are much bigger or much smaller than what we're dealing with in everyday life. For instance, just an example of why we would want to use scientific notation. If you had 12 old nickels in your hand, that is, I say old nickels because nickels used to be made out of nickel metal. They aren't anymore, but that's how they got the name nickel in the first place. So if you have 12 old nickels in your hand, you might wonder, how many atoms of the metal nickel do you have in your hand? Well, the answer is I thought I was going to run out of room there for a moment. So fortunately, I managed to do it. That is approximately the number of atoms of nickel that you would have in your hand if you held 12 old nickels back when they really were made of nickel. That's a very inconvenient number to have to deal with. This is the way that we normally write numbers, but when we normally write numbers, we're writing numbers that are of more convenient size, like maybe hundreds or thousands at the most. And this number here, in order to have any idea what the magnitude of this number is, you'd have to sit there and count all those zeros. There are 21 zeros after the 2, by the way, but you would have to count them in order to know that. Expressing this number in scientific notation gives you 6.02 times 10 to the 23rd power. That is also not really a really nice number to deal with, but it's a lot better than the original number. 6.02 times 10 to the 23rd is compact. You can write it in a small space, relatively small, and you can actually appreciate the magnitude of the number at a glance without having to count all those infernal zeros. So 10 to the 23rd, that's what you need. Sorry. Also, scientific notation usually has the effect of eliminating non-significant zeros. So like when you have a small number and you have a bunch of zeros at the beginning that are really just there to locate the decimal point, those zeros disappear when you put the number in scientific notation. So, so let's go on to scientific notation. So the form of proper scientific notation, it takes the form of a number that's greater than or equal to 1 but less than 10, so basically a number between 1 and 10, times ten raised to a whole number power. This first part of the number here is known as the decimal part. Or coefficient part of the number. And the 10 raised to a power is known as the exponential part of the number. And so anytime you have a number that you want to change it into scientific notation, it basically has to take this form. And you have to manipulate it by moving decimal points around to get it into this form. Okay, just to set us up, 10 raised to a whole number power. That power can be positive or negative. And just as a reminder, what does it mean to raise a number to a power? Well, what it means is you have the number that many times and you multiply them together. So for example, 10 to the first power is equal to 10. That is, you write the number 10 down once and you multiply them together. Well, you don't have to multiply if there's only one, of course. 10 to the second power is where you write 10 down twice and multiply them, and that's 100. Ten to the third power is just 3 tens multiplied by each other, and that's 1,000. and 10 to the fourth is 10 multiplied together 4 times. And that's 10,000. If 10 is raised to a negative power, what that means is that you write 1/10 down that number of times and multiply. So for example, 10 to the minus 1 equals 1/10, or 0.1. 10 to the minus 2 equals 1/10 times 1/10, or 0.01. 10 to the minus 3 is 1/10 times 1/10 times 1/10, or 0.001. And so on, and so on, and so on. I think you get the point. One thing we didn't mention is, what about the 0 power? Any number to the 0 power is 1. That's a definition in mathematics. It doesn't matter what the number is. If you're raising it to the 0 power, it's 1. So 10 to the 0 power is 1. And that actually helps if you need to look at the possibility of maybe changing numbers from decimal to a scientific notation or back again in a step-by-step fashion. You can keep in mind that 10 to the 0 power is 1, and therefore any number can be multiplied by 10 to the 0 power, and it doesn't change the value. So an important skill is to be able to convert between decimal forms of numbers in scientific notation. And so to go from decimal to scientific notation, and we'll see in a little while how to go the other way, the math handout gives some directions for that. I think that the way the directions are phrased can be a little confusing. So feel free to use my procedures here. Either way, you'll end up with the same result. I think mine is a little more straightforward and easier to remember. So converting from a decimal form of a number to the scientific notation. Well, what you have to do is move the decimal point until the number is between 1 and 10. Then you have to multiply by 10 raised to the power equal to the number of spaces that you move the decimal point. Now, deciding whether the exponent, that is the power of 10, should be positive or negative can be a little difficult using the rules as they're usually stated. But I think that if you think of it like this, it might be a little easier. If moving the decimal point makes the number smaller, then the exponent is positive. Because you're not trying to change the value of the number, you're just trying to express it in a different form. So if one part of the number gets smaller, another part of the number has to get bigger to compensate so that the value stays the same. You basically want things to even out between the first part of the number and the second. So moving the decimal made the number smaller, so you compensate by make using a positive power of 10. The opposite is true also. If moving the decimal point makes the number bigger, the exponent should be negative. And that is because you made the number bigger by moving the decimal point. You have to compensate by making the exponent smaller. So for example, changing the number of 1,483 to scientific notation. We have the number here as 1,483. Very often, especially if it's a large number, you will not see a decimal point in it. But if there, again, if there's no decimal point in the number, you can assume that the decimal point comes at the end. So you can actually write it in for the purpose of moving it. In order to get this number to be between 1 and 10, you have to go to the left. You move it one space, you got 148.3. Nope, that's not between 1 and 10, but it's closer than 14.83. Nope, 1.483. That is between 1 and 10. The 1.483 is greater than 1, but it's less than 10. And we multiply this by 10. We move the decimal point 3 places. And when we move the decimal point, we made the number smaller, so this will be a positive 3. You normally wouldn't write the plus in there if it's a positive number, but I did just to emphasize it. If you're not accustomed to doing stuff like this, it might be easier if you try the procedure step by step at first, and then try to do it all at once like I did. So going step by step, you can start out by considering the number to be itself times 10 to the 0. You can do that because, remember, 10 to the 0 is just 1. You can multiply anything by 10 to the 0 without changing the value. So 1,483 is 1,483 times 10 to the 0. That's perfectly true, perfectly valid, kind of redundant, but it's not wrong. As I said, the decimal point is at the end of the number. What happens if you move the decimal point one place to the left? You have 148.3, which is getting closer to being between 1 and 10, but it's not there yet. But by moving that decimal point one place to the left, you made the number smaller by a factor of 10. The way you can compensate for that is by making the exponent bigger by a factor of 10. So 1,483 is equal to 148.3 times 10 to the first. You can try moving the decimal point one place to the left again, and then you get 14.83. And that makes the number smaller again by a factor of 10. And so you have to compensate by making the exponent bigger by 1, which is effectively making the result bigger by a factor of 10. So 1,483 is equal to 14.83 times 10 to the second. It's actually the same value. But this is not proper scientific notation yet, so you have to move the decimal point one more time to the left. And we have 1.483 times 10. Moving the decimal point again made the number smaller by a factor of 10, so we have to make the exponent bigger by 1. And so we end up with 1.483 times 10 to the third. And that is what we got doing it all at once up above. So you can do it either way, whichever way makes more sense to you, and you should end up with the right answer. For smaller numbers, like say 0.0821, we'll call it 0.0821, you can do it directly by taking the decimal point and moving it 1, 2 places to the right. which gives you 8.21. That is a number between 1 and 10. And then you have to multiply that by 10 raised to a number. The number is the number of spaces you move the decimal point, which is 2. And notice that moving the decimal point made the number bigger, which means that you use a negative number for the exponent. So it's 8.21 times 10 to the minus 2. One thing you can also remember is that positive exponent means the number is greater than 1, and a negative exponent means the number is less than 1. Or in other words, big numbers have positive exponents, small numbers have negative exponents. We could do this step by step also. So we have 0.0821, which, is the same as 0.0821 times 10 to the 0. Because again, 10 to the 0 is 1, and it doesn't change value. You can multiply any number by 10 to the 0, and it stays the same. Move the decimal point one place to the right, and you have 0.821 times 10 to something. Moving the decimal point to the right made the number bigger. 0.821 is bigger than 0.0821, and so you'll have to compensate by making the exponent smaller. So it goes from 0 to -1. We don't have a number between 1 and 10 for the first part of the number yet, so we have to do this again. 8.21 times 10 to something. Now we have a number that's between 1 and 10, and we made the number bigger again by moving the decimal point. That means we have to make the exponent smaller again. So it's -2. 8.21 times 10 to the -2, which is actually the same number we got before. So that's how you can do it step by step. Converting from scientific notation to decimal point means basically what you have to do is you want to move the decimal point the number of places indicated by the exponent. If the exponent is positive, what you want to do is move the decimal point in the direction that makes the number bigger. Now, remember what I said. Big numbers have positive exponents, small numbers have negative exponents. And if the exponent is negative, then you move the decimal point in the direction that makes the number smaller, because small numbers have negative exponents. Okay, so say an example like this. Say 3.355 times 10 to the third. Well, what you're going to want to do is move the decimal point 3 spaces, and you do it in the direction that makes the number bigger because you have a positive exponent. So 1, 2, 3. And we have 3,355. You can do this step by step. And doing it step by step is what you want to do is basically move the exponent or move the decimal point until the exponent is zero, and then drop that part of the number, because 10 to the 0 is 1, and you can drop it. So if we have 3.355 times 10 to the third, and what we want to do next is get the exponent to be 0. So if we're going to do it step by step, we would next go from 10 to the third to 10 to the second. When we go from 10 to the third to 10 to the second, we're making the number smaller, so we have to move the decimal point in the direction that makes the first part of the number bigger. So we have 33.55 times 10 to the second, which has the same value as the original number. Next, we want to make it so that it's something times 10 to the 1. Again, but going from 10 to the second to 10 to the 1, we're making the number smaller, so we have to move the decimal point in a way that makes the number bigger. So 335.5 times 10 to the 1 is the same as these first two numbers. Our next step takes us down to 10 to the 0. Again, we made the number smaller by changing the exponent, so we have to make the first part of the number bigger by moving the decimal point. So it becomes 3,355 times 10 to the 0. Now you're done. 10 to the 0 is just 1, so you can drop it. And this is your decimal form, which is the same as what we got when we did it all in one step. An example with a smaller number might be something like 2.65 times 10 to the minus 2. So again, if you want to convert this to a decimal form, you would have to move the decimal point 2 spaces. Since the exponent is negative, you move it in the direction that makes the number smaller, which means to the left. 2 spaces to the left. So the decimal point ends up here, and you fill in any empty spaces with zeros. So we end up with 0.0265 as our answer. You can also do it step by step by counting down the exponents like we did before. Except this time you're actually counting up the exponents, because -2 is below 0. So when you're getting closer to 0, you actually have to go from -2 up to -1, and that makes the number bigger, so you have to move the decimal point in the direction that makes the number smaller. So we have 2.65 times 10 to the minus 2 is equal to 0.265 times 10 to the minus 1. Then when you move to 10 to the 0, that's actually a step up. That also makes the number bigger, so you have to move the decimal point another space to the left. And that gives us 0.0265 times 10 to the 0. 10 to the 0 is just 1, so you can drop it, and 0.0265 is your decimal form. So that's a quick lesson on scientific notation and how to convert back and forth between decimal and scientific notation. That's all the time we have for this particular segment of the lecture, but I'll be back momentarily with the next part. So I'll see you then.